these two properties up for you about how you show whether a function's even or odd. And you had to extract this from your memory because, you know, we probably talked about this maybe 3 weeks ago, and that's like 10 years ago, right? But if you had to extract this from your memory or try to hold on to what is it that I have to do to show that something may be even or odd, a function may have even or odd symmetry. Is there any like picture in your brain that you recall about either of these ideas? Is there anything that goes on that helps you? Yeah, Felicia? Looking at the exponents. Okay. And what did you remember about that? Okay, so you remembered that there was something to do with the exponents being even, then the function was even. And then if there was an odd exponent, it was odd. So that's kind of true, but not totally, because if I change this function right here to be x to the fourth minus 2x plus 1, then it has a combination of even and odd. So what do we do then, right? So what's sort of like the parent functions that you might think about, Felicity, that would have like an even function and an even exponent and an odd exponent, like the basic ones that might help you recall this? What's the first one that comes to your mind when you say even exponent? The easiest one. X squared, right. So if you just keep in mind this picture of x squared, which is coming back to Felicia's idea, it has an even exponent and it's the parent function, right? We can do lots of different quadratic functions, but that's like the basic one. And you just try to recall something about this. Now, if we think about this, we know we get a sense that this has symmetry about the y-axis, that we can fold this right in half. But the property that you're looking for is that if you take, and we'll keep this like with numbers. So if we take a 3, which is to the right of the vertex, and then its opposite, which is to the left of the vertex, exactly the same distance, what's the property that we're looking for? Is that they're both exactly the same height above the x-axis. That if I take a number, a value for x, and I put it into my function, the output is exactly the same as the output if I put the opposite value into the function. And that's what this says. Take any x, put it into my function, out comes a y value. If I put in the opposite of that number or that value and I put it into my function, these two things are equal. That's what it means to be even. So let's do that. But we got to do it. Remember, we can't do it for numbers. We have to do it for all x's. So if I already know what f of x is, so I can already do the right-hand side of this equation. So it's x to the fourth minus 2x squared plus 1. That's f of x. So I'm still trying to determine if that's the same now of taking this function and I replace my input x with the opposite of x. So remember, you have to put that in parentheses. Okay, and if I take the opposite of x, which is really the same thing as -1 times x, and I raise that to the fourth power, I'm going to have -1 times -1 times -1 times -1, which is 1, x to the fourth. And -1 times x squared is x squared. And as you can see, Felicia's idea works here, because every time you put the opposite in, as long as all your exponents are even, it's going to come out to look just like when you put in x. So this is an even function, so you don't even have to bother with the right-hand side. It says it's an even function, so it has symmetry about the y-axis. All right. Now, I did a little picture here for you of this function in GeoGebra. I just threw it into GeoGebra, which is such a neat little program for us in terms of getting a picture of these things. Let me come back here. So Let's take this, get out of my way. And these are the types of graphs we're going to be creating now. This is a graph of a polynomial function. So I'm going to just replace the odd stuff over here with it. Okay, so this has a few more hills and valleys than what we've traditionally been looking at, but you can still see that this function has symmetry about the y-axis. You can fold this in half right over the y-axis, and whatever point we have on one side has a matching point on the other. Okay. Couple things to notice. We have 1, 2, 3. We call those things turning points because the graph turns at those points. So we have 3 turning points here. And we've been calling those turning points relative minimums and a relative maximum. Okay, so we have 3 relative minimums and 3 relative maximums, which are turning points. All right, and then these other ideas we're going to look at today, we're going to explore that the fact that at -1, this function turns around, it's decreasing until we get to -1, and then we increase. Then we decrease, and then we increase. So that's what we mean by turning points. The function prior to that turning point had been decreasing. After that turning point, it's increasing. Then it decreases and increases. Okay. So I'm just going to mark that with, I'm going to say that on this interval from -infinity to -1, remember we always use open intervals when we talk about increasing and decreasing. Our function is decreasing. From -1 to 0, our function is increasing. And from 0 to 1, our function is decreasing again. And then from 1 to infinity, our function is increasing. What's the domain of this function? What's the domain? Right, -infinity to infinity, all real numbers. That's the beautiful thing, excuse my weird language, about polynomial functions. You never have to think about the domain. Any number, any real number can be put in there. There's no limit. Why? We don't have anything like square roots, so we don't have any denominators to worry about. So polynomial functions have a domain that's always all real numbers. What about the range here? How would you describe the range on this? So the domain is all real numbers, -infinity to infinity. What about the range? Can you help me with that, Jacob? Right, 0 to infinity. Right. The other thing we're going to be talking about today is the fact that notice that as x gets bigger and bigger, grows without bound, and as x gets smaller and smaller, this function has both of its arms up in the air. Let's make one little change to this and see what happens. That's the fun thing we can do with GeoGebra. So let's check out, I'm going to take that function off by taking this little blue dot and just clicking on it. Let's see what happens if I call this g of x. And now I keep basically, it's going to look the same, but I'm just going to make this coefficient in front of x4 a -1 instead of a +1. In your mind, think about what you think might happen to this function. I won't ask you to divulge your secret ideas. So we've put that function into GeoGebra. Let's see what we get. Oops. I can't even see it. Well, we'll just make it smaller and smaller and smaller. Oh, that really changed the picture, didn't it? Oh, that's why it's so weird. Thank you. to square that 2x. All right. There we go. Now we're okay, right? But what's the difference? If we keep going and going, what happens to the value of y, our f of x, as we go to the right towards positive infinity and to the left? Where's it going? It's decreasing. This one, both arms, I call them arms. Both arms are up. This one, both arms are down. What's the major difference between these two functions when I entered them? What looks different? Right. Somehow we lost all those turns, right? When I compare these two functions, is there any indication that in one of those the arms were up and the other one the arms were down? Anything you think, what did I change there between those two functions? No, right. This one, what's the coefficient of x to the fourth? What's the coefficient? What's the number that multiplies x to the fourth here, even though it's not in there? And what is it here? -1. So x is still the same. It's just that I have a -1 out front. That's what we call the leading coefficient. That's going to be some of our new terminology today. So here your leading coefficient, because this is the term with the highest exponent. So the number that multiplies it is the leader of the pack. So here it's positive, here it's negative, and we'll explore that more in today's demo. So let's take a look. I just wanted to give you a little flavor for the types of things we're going to be graphing now. All right, so we've already studied two types of polynomial functions: linear, where the highest exponent you see is 1. So f of x equals x to the first power is going to have even symmetry or odd? What do you think, Felicia, based on your hypothesis? Odd, right? Because if you put an x value in, think about f of x equals x. If I put 2 in, I get 2. When I put the opposite of 2 in, I don't get 2, I get -2. You have opposite outputs, and that's what odd functions have. So now we want to look at stuff that can be polynomials that can be of any degree. And this definition can look a little like scary when you look at it, but we have to have a way of representing any polynomial function. So let's take a look at this. The coefficients are a sub n, a sub n minus 1, and then as we get close to the end, we say a sub 2, a sub 1, and then a sub 0. This is just going to be a constant. This is your constant term right here. Because if we put it in, if we put the variable in here, it would be x to the 0 power, right? X to the 0 power we know is 1. So that's why we don't bother putting in the x, but we could. So notice what happens. We go from our biggest exponent n, and each term after that we could decrease that exponent by 1 all the way down to 0. But we can't just put in every possible polynomial in the world. We'd be here until we died. So this is just our way of representing any polynomial. If I take my hands and cover up everything until we get to a sub 2x squared, that would be a quadratic function. If I covered everything up to there, it would be a linear function. So if I wanted to make this a third power, a fourth power, or a fifth power, I need to have some way of representing that. So notice, the higher the power is, whatever the highest power is, n, the leading coefficient here is called a sub n. Notice the subscript on the coefficient and the power of your x match. Okay? That's how we distinguish from one coefficient to the other. Without changing, we can't say A, B, C, D, E because we only have 26 letters in the alphabet. I could have a polynomial that extends across this room, so I would need more letters than 26. So that's why we refer to them with these powers and their leading coefficient. They match. All right, so let's take a look at this. Again, A sub n, whatever your highest degree is in your polynomial, the coefficient before it, A sub n, is called the leading coefficient. That's right here. And the other really big idea here that distinguishes this function from other functions is that your powers, your exponents, are non-negative integers. That means they're 0, 1, 2, 3, 4, 5, 6, 7, all the way to infinity. Non-negative, so they're whole numbers. Okay, they're whole numbers. So you'll never see a negative exponent. You'll never see an exponent with a fraction in it. Okay, so these are kind of the more friendly functions to graph. They don't get too wild on you. Okay, so let's take a look at some of the examples that I've put down here. We're going to save this last column. We're not going to fill this in yet. But let's take a look at these polynomials and let's give them some names. So first of all, what name might you give to this polynomial? It's not quadratic and it's not linear. Do you know what we would call, Gabe? Third degree. Yep, we could call this a third degree polynomial. So we haven't even discussed what degree is, but we'll get there. What other name might we give to a third degree? What, when you look at the volume of something, what kind of units are on volume? Cubic. So this is also called a cubic polynomial. All right, so the degree of a polynomial, regardless of the order that each of these terms are in, is the highest exponent you see. It's the highest exponent. So this is what we call a third degree. Okay. This particular polynomial is also what we call in descending order. We start, the first term, x cubed, is the highest exponent, and then we proceed to the next smallest exponent, the next smallest, till we finally get a constant. Now remember, there's no rule saying if I have a third degree, I have to have a squared term in there or a linear or even a constant. The coefficients after x cubed, the coefficients could be 0 for all of them, and you could just have f of x equals x cubed, which you graphed in your project. That was the very first function you graphed in your project. Okay, what's the leading term? The leading term. Terms are the parts of addition and subtraction, and polynomials are a bunch of terms added and subtracted. So what's the leading term here other than Gabe, who just answered the first question? X cubed, right? X cubed. Okay, what's the leading coefficient of x cubed? 1. And what's the constant term? 4. All right, we're going to save this column. Okay, so at your seats, I want you to fill in the rest of this chart, and then we'll go on to the rest of the demo. So what kind of form is this last polynomial in? Factored form, right? So this is in factored form. Listen to this incredible language that we're coming up with, huh, Doug? So in order to answer these questions, you have to put it in polynomial form. So you've got to convert this to polynomial. But let me give you a little clue. You have to convert it to polynomial to maybe answer these other ones unless you can do all this factoring multiplication in your head. However, in factored form, you can still come up with the degree of the polynomial because notice, this is the second degree. What would be the exponent on the factor x plus 2? What would be the exponent on that? Even though it isn't there. 1 and 1. So if it's in factored form, if your polynomial is in factored form, which is what's going to happen on your projects, your next project, you add the exponents of each of your factors to get your degree. So we got an x, and that's because look, if you take x plus 2 times x minus 2 and you multiply that, you're going to get x to the x squared minus 4. And then you multiply that x squared by this x squared, it's going to give you x to the 4th. So when you're looking at a polynomial in factored form, you have to add the exponents for each of your factors. So if you multiply that all out, it's going to look like this, which then means it's going to look like this. Okay. So the leading term is negative x to the 4th. There is no constant term here, none. So you could put the plus 0 in there if you want. The leading coefficient's negative 1. Okay. All right, so unfortunately that's taken a little more time than I wanted to, but there's a lot in there. So let's talk about the behavior. This is a really, sort of big idea that we're going to talk about with polynomial functions, and it's called the end behavior. All right, so this is the end. Do, 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 do. I should find that Beatles song. All right, so the behavior of the graph of a function to the far left or the far right, we talk about as x goes towards infinity or negative infinity, or as x increases without bound and decreases without bound. What happens to each of these graphs? Every polynomial function, every single one, eventually is going to rise or fall as you move to the right. And if you move to the left towards negative infinity, it's either going to fall or it's going to rise. That will always be true for any polynomial function. So again, just like with the even and odd idea, all you have to keep in mind is two functions. Your first degree function, which is a straight line, and your parabolas, right, of degree 2. All straight lines are either going to look like this or like this, right? I know I kind of look silly here doing this. Straight line's either going to be like this with a negative slope, so your leading coefficient's negative on a straight line, or positive. When you're negative with an odd function, odd degree, your right arm is always down. When you're even, when you're positive slope, your right arm's always up. Now let's look at quadratics. This is the happy parabola with the leading coefficient positive. Both arms are up. Yay, touchdown. When your quadratic function has a negative coefficient, it's sad. Both arms are down. This works the same way whether we now look at a 3rd degree and a 4th degree, a 5th degree and a 6th degree, a 7th degree and an 8th degree. Get what I'm doing? All you have to remember are these two functions that you're very familiar with. So if the leading, if it's an odd degree function, that means your highest power is odd, it's going to have end behavior like one of these. If it's an even degree function, it's going to have end behavior like one of these. Either both arms are up or both arms are down. How do you know? The leading coefficient will tell you. On this one, the leading coefficient, which is your mx plus b, that m is your leading coefficient. When it's positive, your right arm is up, your left arm is down. When your leading coefficient here is negative, your right arm is down, your left arm is up. Okay? So let's take a look at this. End behavior means the x's are going all the way out here. Where's my y value going? X's are going all the way out here. Where's my y value going? It's the very ends of your polynomial. And often we just indicate that idea with these arrows. We never go out that far. Okay? So let's look at the notation now, because the notation is a little strange, but you'll get used to it. So to talk about this end behavior, we're talking about the x values increasing without bound and decreasing without bound. So right here, as x goes to negative infinity, the output f of x, or what we call y, is decreasing without bound. So that goes towards negative infinity. Now notice the language your book gives you. As x decreases or moves towards negative infinity, this falls to the left. It decreases. As x goes towards positive infinity, that function increases without bound. So that's infinity. Right, now the next function, everything's just reversed. As x gets really, really small, my function's increasing forever and ever. So that's infinity. And as x gets really big without bound or moves towards positive infinity, this function's decreasing forever and ever and ever. So that moves towards negative infinity. So you'll be using this symbolism as you describe functions. Now let's take a look at the parabola. What happens to this? What happens to f of x in this parabola as x increases and decreases without bounds? What happens to the value of f of x? What does it get close to? As x gets really big or really small? Positive infinity. Notice these will be the same always with even degree functions. This will always be the same. Okay? Because either both arms are up or both arms are down. Okay, and then in this case, both arms are down, so the output is moving towards negative infinity. Any questions on that? I know it's a new idea, this idea of end behavior. Now here you see we have degree an odd degree 1. Here's an odd degree 3. Look, here's your cubic function, which is the first function you graphed. I just want to talk about this. Notice with the odd functions, at the x-intercept, your function goes from being a negative output to a positive output. Both situations here, positive to negative. Your output changes sign once it crosses over the x-axis. Goes straight through when your degree is 1. Here, it's crossing at 0, 0. And it flattens out. It doesn't become totally horizontal. It's actually getting closer and closer and closer to the x-axis. And it sits on the x-axis at 0, 0. But again, you're changing sign. Here, your output is negative. Here, your output is positive. That's something to notice about odd degree functions. So here, this idea, if you have a straight line in mind with positive slope, this exactly works the same way. This function will be negative infinity and positive infinity. Right arm is up, left arm is down because our leading coefficient is positive. Here, as we move towards negative infinity, we move towards infinity as our output and negative infinity as our output as x grows without bound. It's a lot of language. So here's a quartic function. That means fourth degree. Notice both arms are up or both arms are down. These are both up and these are both down. So there's a lot going on here for you to look at, especially in the quartic function. Notice that it has similar to the one we looked at the beginning, it has 2 valleys and 1 peak, relative max and 2 relative mins. This one, look, it looks like if I took off everything from 1 to infinity here, that almost looks like a cubic function, doesn't it? Flattens out right there. So that's interesting. All right, so this is all totally summarized for you right here. So this is something you should have. This is taken right out of your book. So I'm not going to go through that because we just did. All right, so when you get to your class activities, I want you to go back and fill in the last part of that table in problem number 2. Not right now, because we still have to talk about a couple more things. Okay, find all the zeros of this function. What is a zero? When the function equals 0, when f of x is 0, so we call it a zero of the function. A zero of a function is a value of x that makes your function equal to 0. So it's a solution to the equation. So zeros, when you list them, should be listed as solutions. You can put it in a set, or you could say x equals. What we traditionally call zeros, what we think of in our mind when the function's equal to 0 is x-intercepts. So it's just a new name for an old game. All right, the zeros of a function is where your output is 0. Think of a graph. Your output 0 means you're sitting on the x-axis. So you've done this over and over again. You set your function equal to 0, and then you solve the equation for 0. Since that's a cubic equation, it's a polynomial equations, we did these way back in chapter 1. The only way you can do this is to put it in factored form and then set each factor equal to 0. And the only way to factor this is that famous friend of yours, the greatest common factor. So you pull out x, and then you're left with a second factor that can be factored as x minus 2, x plus 1. And so when you set each of those factors equal to 0, you get x equals 0, 2, and -1. You set each factor equal to 0. Okay, you've done this quite a bit. All right, so the zeros of this polynomial are 0, 2, and -1, which means if you graph that polynomial, let's pull out GeoGebra once again. All right, so notice these zeros, x equals, and my math lab, whenever you solve an equation, they call a solution set. So another way you might write this if you were doing this in my math lab is just to put the 3 solutions to the equation in a set like this. Or you could just say x equals each one of them. These correspond to the following x-intercepts, which you can see located right here on your graph. Now notice at each of these x-intercepts, your function changes sign. And at -1, before -1, it was negative, then it turns positive. And then it goes from positive to negative and negative to positive. Okay, and that's because each of these factors right here, this is another idea of polynomials. When each of those factors has an odd degree, you're going to be changing the sign when you cross over. You're going to be crossing over the x-axis at each of those points. Okay. So that tells you here, here, and here, you change sign. Your function changes sign. All right. So the last idea, there's a lot of ideas in polynomial functions, and I apologize. It's a big idea. You know, it's a lot of material. Is this idea of what happens at these zeros. So right here is a 0. The 0 of this function is 1. The 0 of this function is 1. At this 0 right here, notice if you just blow up that area right in there, I think I need my magic pen for this to see. Let's blow this up if I can find my magic pen. My magic pen is right here. If you just blow up that area of the polynomial, if you blow that up, what kind of function does that look like? One that we just looked at earlier. Is it a straight line? Does it change sign from one side of 1 to the other? That means it has to be odd. So is it does it look like a cubic function? Yeah. So notice at that 0, this flattens out, which tells you that it has an odd degree. Notice this is in factored form. Look at what the degree is right there. It's odd. Let's take a look at this other one. Let's blow up this right around that 0. What kind of function does that look like? Quadratic. It looks like your parent function, doesn't it? Okay. So that has an exponent that would have to be even. So this is an idea, the last idea we have to talk about with polynomial functions is not when we talked about end behavior way out here. What happens near those zeros? What happens to the function near those zeros? If the function is just touching the x-axis there and going on its merry way, whether it was decreasing and then increasing, or whether it was increasing and then decreasing, then it just touches it, just gives it a little peck on the cheek. Doesn't change sign. Notice this parabola is all above the x-axis, so all your outputs here are positive. Doesn't change sign. Then we say in factored form, if you take your polynomial and it's in factored form, its exponent must be an even exponent. When that happens, we say this factor occurs twice. At that zero, it's going to stay. If it was positive before the zero, your output's going to stay positive. You just touch it. When this factor occurs 3 times, it's odd. In this particular case, the function approaches that zero, flattens out, and then changes sign. It actually crosses over from being below the x-axis to the above the x-axis. The name we give to this, the fact that these factors occur twice or 3, is multiplicity. That makes sense because you could multiply this 2 factors, and this would be, when you multiply it out, 3 factors. So it's called the multiplicity of the zero. So the multiplicity of a real zero tells us about the graph's behavior near the x-intercept. It's the behavior of the graph near the x-intercept, or the zero of the function. If the multiplicity is even, like right here, then the graph touches the x-axis at that zero. Doesn't change sign. If the multiplicity is odd, like right here, we cross over the x-axis at the zero. If the graph crosses the x-axis in a linear fashion, which we don't have, like right here, notice if I blew up the behavior near those 3 zeros, it would look just like a straight line. If it crosses straight through like a line, then we know the multiplicity has to be a 1 on that factor. If the graph flattens out as it crosses, it's starting to flatten out right here. It gets a little flat, flattens out. Then it's got to be a multiplicity. It's got to be a multiplicity higher than 1. It might be 3, it might be 5, it might be 7. Okay, and here's a note. In order to determine the multiplicity of a zero, you have to have it in factored form. Okay, you've got to have it in factored form in order to determine the multiplicity. That's a lot, and I'm sorry, but there was a lot in that section of the book. You have quite a bit of time. Oh God, I'm still not done. Let's do this. I want to show you how to graph a polynomial. Here's your polynomial. Well, let's look at Felicity's idea. Oh shoot, Felicity's idea isn't going to work because it has even and odd in there. So it's not going to be an even, in other words, it's not going to have symmetry about the y-axis. But because the degree is even, it's either going to have both arms up or both arms down. The leading coefficient is positive, so we know when we graph this, both arms are going to be up. That's what we can tell right away from looking at this. Okay, so we know what the end behavior is. The end behavior right away says as x goes towards positive infinity, my right arm is up, and as x goes towards negative infinity, my left arm is also up. And that's how we say that in symbols. The next most important idea is to find the zeros of the function, or what we traditionally call the x-intercepts. So we set this equal to 0, and we play the same game we just played a minute ago. We factor this. I pull out x squared as my greatest common factor. And then this gets a little boring after a while because you've done it over and over. And what's really critical about this thing, when you look at this, you may not know right now, but this is a perfect square trinomial, because the factors of 9 that add up to 6 are 3 and 3. So we're going to end up with duplicates here. So if you rewrite this, you could rewrite it like this. X squared times the quantity x minus 3 squared. This is factored form. Notice if you add the 2 and the 2, you come back to your leading degree of 4. In factored form, you can add the exponents. When it's in polynomial form, you just look for the highest exponent and pick it off to determine the degree. Okay, so what are the solutions to this? X being 0 and x being 3 is the solution set. So that means 0, 0, and 3, 0. Something's going to be happening with this polynomial. Okay, those are the x-intercepts. So let's put them in here. 0, 0, and 3, 0. Well, it's always good to find your y-intercept. That's when x is 0. But we can see from looking at this, it doesn't have any constant terms. So that means 0, 0 is acting as both the y-intercept and the x-intercept. Right. What do we know about this from the end behavior? We know the right arm's up and the left arm's up. So I'm going to rewrite this in factored form right beside it because that's really what's most helpful in terms of graphing. Now here's the key idea. When we set that factor equal to 0, it gives us 0, and that one, it gives us the 3. So what's happening at these two zeros? They're being kissed. The multiplicity of this factor is 2, and the multiplicity of that factor is 2. Just think in your mind about a parabola. Just think of x squared. It just touches at each of those points. It doesn't cross. Just gives it a little peck on the cheek and continues on its way. That's all you have to remember. So you're just getting a sketch here, folks. You're not getting accuracy. All you do is you say, okay, here's my left arm. I'm coming down to this 0. And because I have multiplicity of 2, oops, I don't do that. I don't cross. I just make believe I'm a baby parabola and I just head along out back up. Now, I don't care how high I go right here. I'm not looking for accuracy. But I know at 3, I've got to come back down and kiss it again. And off I go into the wild blue yonder. You see? That's all you do. So the fact right here, you have even multiplicity at both of these points. So your graph, that's right here with these 2's. That means your graph just turns right around. Okay, it looks like a W. And again, this thing could come way up here, this relative maximum, or it could be right down in here. I don't know. I mean, I could throw it into GeoGebra and find out. That's it. That's all you need. Go to town on your class activities.